So welcome everybody. This is Flow seminar, where Flow stands for Federated Learning One World. This was a seminar that was created to provide a global online forum for the dissemination of the latest scientific research results in all aspects of federated learning. Today is my great pleasure to introduce you our speaker, Ziyue from NVIDIA, who is currently senior scientist there. Before that, he was a staff scientist and lab manager at National Institute of Health in USA. His research interests lie in the area of image analysis and computer vision with applications in biomedical imaging. He has been working on collaborative medical AI development over the years, along with fellow researchers and clinicians. He's IEEE senior member, area chair for major conferences, and associate editor for several journals, including IEEE Transactions of Medical Imaging and International Journal of Computer Vision. And today he'll tell us more about federated learning in the age of foundation models. So great pleasure to have you, Ziyue, here, and please go ahead. We're looking forward to your talk.
Thank you. Thank you for the invitation and introduction. I'm Ziyue from NVIDIA. I'm a researcher in federated learning and computer vision. So today we're going to talk about federated learning in the age of foundation models. Mainly, we'll discuss what are the new challenges and new opportunities for the federated learning with regard to large language models and more broadly, foundation models. So today's agenda, we'll first cover the relationship between foundation model, what are the new opportunities, and federated learning. And following by the introduction, we'll discuss a few key items. One is the new fine-tuning and training shifts from the traditional deep learning model training. We'll also talk about what if the large language models are totally used in a black box fashion, what we can do towards a better utilization of the large language models. And also, following by that, we'll discuss the most recent generation shifts, that is the retrieval augmented generation. And finally, I will discuss how we want to perform the real-life federated learning studies using NVIDIA FLAIR as the backbone platform. So let's start it by talking about foundation model and federated learning. What are the new challenges and new opportunities? So foundation models actually gives, as we know, gives pretty decent performance over a wide range of tasks. So in this age, why do we still need federated learning? Is it benefiting the large language models and other foundation models? To the motivation of performing federated learning, as we know, is to break the barrier of the data resources that can most of the time be restricted by the strict sharing policies. So that even if the foundation models give pretty decent performance over the downstream tasks, they can still be limited in their performance over certain domain-specific tasks. So those are calling for more further fine-tuning with the task-specific data. And in the meantime, for a foundation model being foundational, the need for data is very prominent for it to cover the majority of use cases, to cover potential variations. The more data for training is better. So it's like other deep learning techniques. More data could help building a different large language models or foundation models towards better accuracy and better robustness and generalizability. So this is actually a must for being foundation from the basic perspective. But of course, as we know, data can not be centralized in many large language model tasks. For example, the reports from different hospitals or financial data from different institutions. They are most of the time, they're restricted from being shared to others and being centralized for model training, mostly because of the privacy and regulations, and also caused by the geopolitics and copyright restrictions. And well, in this age of foundation models, the amount of data for training those models can be huge. So there are both the significant effort to move the data together and also the significant effort to train the model. That requires a lot of hardwares to begin with. So in this sense, federated learning provides various options to address the challenges of at this foundation model age from different perspectives. First of all, is the federated training. We can enable the data efficient training of foundation models. And not only that, we can also enable resource efficient training. Considering the one site may not have sufficient computation resource that is enough for train a large language model from scratch. And if we pool all the efforts from several sites together, maybe one site only have, say, one node of H100, but with several sites contributing together, we can build a very good large language model with sufficient enough of data and sufficient enough of computation resource. So in this new age, the federated learning may not be just account for the challenge from the data perspective, but it can also taking care of the challenge from resource perspective. And another thing, the benefits from federated learning is that we can not only get the global model trained, we can also get personalized models, and such that each site can benefit from from the global knowledge, but also tuned towards its own data distribution. That is something that may not be easily achievable if we consider the centralized training. And beyond that, we can also have federated inference or evaluation. Again, that is something pretty unique to large language models because models is growing so big that one site or just the one ordinary hardware may not be able to host the inference. And if we break it down in a federated or distributed way, this will become something that is going to be feasible for a single site or several sites to host. Any questions? Guess not. Okay, then let's continue. So having said that, how actually we want to implement the federated learning to tackle those new challenges? The first of all, as we mentioned, we face significantly bigger models. That, of course, indicates the significantly increased communication costs. For example, now the 70 billion size large language models is the common state of the art. For example, the Llama 3.1 available in 80 billion, 70 billion, and hefty 405 billion versions. Well, 3.2 is as a distilled version. It's have 11 billion and 90 billion. So if we want to perform the regular Fed averaging with those 70 billion models, the communication cost will be huge. And there definitely needs to be something from the communication backbone end to enable such communication, right? And some specific techniques to say lower those communication costs, or some other techniques to work around that. And also, not only that, some of the proprietary model are only available for inference, meaning that we may not be able to fine-tune that using the gradient-based method. So we want to develop some new techniques so that even if the model is only available for inference, we can further fine-tune some of our own encoding schemes so that the encoding will be beneficial for us to get a better performance. And yet another shift is for the training scheme from fine-tuning to say partial adapters. So that is another thing that is new for federated learning in this age of large language models. And of course, as we talk about, there will be new inference patterns from simple inference to retrieval augmented inference. And of course, despite the challenges, federated learning can enable real-life collaborations for breaking both data and computation constraints, because we benefit from the privacy assurance to break the data access limitations to ensure that our privacy will not be broken. And so we can all further enable distributed computation for training by enabling data parallel with efficient data federated schemes like FedOpt and efficient communication. We can even enable distributed inference hosting by enabling different kinds of parallelism with model dissection and execution. So let's take a look at some examples in more details. The first being the training part. So now here we will give two examples, one for supervised fine-tuning and the other for parameter efficient fine-tuning. The supervised fine-tuning SFT is actually the base training scheme for foundation models. It leverages models that have already been trained on large datasets with foundational understanding and will enhance the model's performance on specific tasks or specific generation styles, say instruction following, using the task and site-specific data. This is actually the first step towards the modern large language model for instruction following purposes. Essentially, it's nothing different as compared with, say, our traditional Fed averaging scheme. It is sharing and tuning the entire model and sharing the updates with the global server, where the updates will be aggregated, averaged together, and sent back for local clients to update. So we perform some experiments with three distinct data sets, Alpaca, Dolly, and Open Assistant for this instruction following purposes. The model we use is the NeMo model 1.3 billion and SFT for 5 rounds. So we're going to perform 5 experiments in total, the training on each client's own dataset, so 1, 2, 3. And with a combined dataset, pulling all the 3 datasets together and all 3 clients together using Fed averaging scheme. So let's take a look at the results. We have 3 colors here, yellow, green, and blue. They represent the 3 individual sites. And the lighter version represents the local trainings. So as we can notice here, for the local trainings, they tends to overfit to one site's own data. So because this is the training curve, and we can notice the arrow is growing bigger. While the darker curves here with this step-like observations is the federated learning result, because we sync for 5 rounds. Every time we sync, the global model will combine all the 3 data sets, and global model will look like will sync together. And this curve, magenta curve, represents the training curve using the centralized data set. So as we can see here, although the local datasets, local training seems to overfit to local datasets, if we perform federated learning, the steps showing here, it can remove that overfitting, and also the global model trained with federated learning will achieve similar accuracy as compared with the centralized training. So this is just according to the training curve. Well, it is, as we know, the model performance actually is evaluation is not a trivial task compared with, let's say, fixed downstream task like classification, where we usually have a specifically defined metrics like accuracy or F1 score. For a supervised fine-tuned model towards instruction following, exactly model performance evaluation is actually a non-trivial task. A common practice is to test the resulting large language models on benchmark tasks and all human evaluations, of course. So here we perform the standard language modeling tasks under a zero-shot setting, including these 3 tasks subsets. And with the same number of training samples, combined datasets spanning from more diverse data resources, and present better robustness and performance over individual data models. Well, a federated learning model using Fed averaging further promotes the performance with more data coverage. So as we can notice from this final result, the Fed averaging can achieve the best perform metric on several metrics. So and that is close to the combined data sets trained on the models. So it's shown that Fed averaging can effectively combine the data coverage from different data sources and promote the model accuracy towards this specific task of instruction following. So this is the supervised fine-tuning that
Yeah,
is
sorry,
yep.
CJ. There is a one question in the chat by Andre. I don't know whether whether you want to ask yourself or whether I should read it out loud.
I can ask, it's all right. Thank you.
Sure.
My question was, so I guess it's sort of related to the supervised fine-tuning because on the local data sets, you would presumably assume that each local data set, roughly speaking, in the total data proportion would have the same representation. Now, if you move this, let's say, to a multilingual setting where presumably the clients interacting in the federated training, you will inherently have a bias towards the majority languages. Do you have any viewpoints on this, particularly on, are you worried about sort of the bias towards majority languages to be exacerbated in this setting?
Yeah, that's a good question, good point. Because the unbalance or between different sites is always has always been a problem or challenge for federated learning experimental design. So it's always about who we want to highlight. For example, let's say in previous medical domain, we have one side say holding uh, rare disease, although the whole data set may be small, say it only have 100 cases, but it can hold like 90 cases is rare disease. Well, for another data set, another site, it can contain, say, 1,000 images, but it may only have 10 images that belongs to these rare disease cases. So I guess the answer to your question is really case dependent. For example, it's case dependent because that is something related to what we really want for the output of a federated learning study. If what we really want is to a model that is very balanced towards different languages, then we want to balance the contribution from different clients, maybe evenly distributed, or we can consider which client holds the, like say 10, we have 10 clients and 8 of them are all English based, and then 9 and 10 are some other languages. Then if our ultimate goal is to train a model that handles all the language pretty well, then we may higher the weights for those 2 clients that are holding the languages different from the other languages. But if our ultimate goal is to have a model that works really well on English, but and meanwhile have some capabilities on other languages, then we may use maybe the standard Fed averaging scheme that is solely relies on the sample numbers. And actually, as comparison, that's pretty much the similar to medical imaging cases. If we want, the ultimate goal is to train on the classification of the rare diseases, then of course we do not want to concentrate, give very high weights to the client with many data, but limited amount of rare diseases, the 1,000 data, the 1,000 data one. But we want to give more credit to the client with say 100 samples, right? So we cannot rely on the standard Fed averaging. So I believe the weighting scheme will need to be carefully structured and designed towards the ultimate goal. If we consider different goals of our federated learning study. Yeah, I hope that clarifies your question.
Yeah, thank you.
Thank you. Okay, if there's no further questions at this stage, let's move on to the parameter efficient fine-tuning. So this is something that's pretty new for large language models. That's pretty because previously we want to train a model, we just fine-tune everything. But for large language models, since the foundation models are trained well already, most of the time we do not want to modify it too much because to avoid the loss of generalizability and loss of its capabilities. So unlike supervised fine-tuning where the entire model is being fine-tuned, parameter efficient fine-tuning only fine-tunes a task-specific module. Well, the most of the large language models will be fixed. Only a few dozen million parameters will be exchanged and updated. So this category includes techniques like prompt tuning, p-tuning, adapters, etc., and mainly towards downstream tasks like brainstorming, classification, closed QA, those downstream tasks. And let's say as we noticed, the majority of large language model parameters will stay fixed. Only the added prompt encoder or other adapters parameters will be trained, exchanged, aggregated, and updated in a federated fashion. So in this way, the communication burden will be a lot less, and also the same thing for the training burden. And in this example, we perform p-tuning for sentiment analysis. The prompt learning is with downstream task example is using the financial sentiment analysis. The data set is a financial phrase bank, and the task is to tell the sentiments from some financial news headlines, whether it's neutral or positive or negative. And specifically, more details on the experiment, we use the NeMo Megatron GPT model hosted on Hugging Face. For this, say, 20 billion model, only 50 million parameters will be updated, which consist of only maybe 0.25% of the entire parameter space. And some more details of the training data set and training results we used. And for the results, we can see the accuracy over the task. In this case, the federated learning can achieve the performance that is comparable to centralized training, and in the meantime, better than the local trained models. And one more thing to mention here is that we can even try different parameter efficient tuning options like p-tuning, adapter, LoRa, with only one line of configuration change. And yeah, and we can see their performance curves here. They are pretty different, I would say, if we consider choosing different options to your own applications. And the good news is that it's pretty easy to swap from different options, and you can try different options so that the finally trained model will be best serve your purpose and your candidate task. So another thing let's discuss is this research item called large language model as a black box. So why the motivation here is at this age, when we talk about large language models, many proprietary models or public models, they are mostly served using a inference API, meaning that everyone can access easily, even with just a cell phone, we can access it. And the heavy lifting work will be done in a black box fashion. We send the request, the queries, and then the black box large language model do the computation, and then through this inference API, send back the results. And this inference result is something we have access to, and that is the only thing we have access to. And it is both good and bad. The good thing is that everyone can access, even if your client is just a cell phone. And the best thing is, of course, we don't expect the gradient to be sent back. We don't expect the regular gradient-based fine-tuning. And from a practical perspective, those gradient-based fine-tuning may not be able to be performed by the clients if the client is just a cell phone, right? Even if the federated learning server say, hey, train this model parameter and upload it to me, a client with just a cell phone will not be able to do that. So in this work we call FedBBT, we aim to address this challenge by efficient federated black box prompt tuning for large language models. This is our work in this year's SAML. And this is a very unique challenge in the age of large language models because the clients train prompts while treating the large language model as just a black box. And the clients only conduct inference with the large language model server without the backpropagation, without the knowledge of gradients. And then clients upload and download the prompts with its own encoder to and from the federated learning server rather than the whole model. So the aim is to learn a optimized prompt encoding scheme in a federated fashion for prompt training. Well, this learning will utilizing gradient-free optimization methods rather than with gradients, because that is something we are not able to do under this black box setting. So the method we use is the gradient-free optimization for the with federated global estimation using the evolution strategy for optimization over the optimal prompt distribution. So we start with the local distribution and with several inference and optimizations, the local distribution will be slowly converged to an optimal distribution. But since what we get is a distribution, we cannot rely on simple averaging to tell the global distribution, optimal distribution, because as we know, if we have several distributions that are quite different from each other, simply averaging them together will not give us the optimal global distribution. So rather than simple averaging, here we perform a global prompt distribution searching with awareness of local prompt distributions, such that the global model will gradually converge to a optimal solution. And this is the key part of our proposed method. One is using this gradient-free evolution strategy for local and global optimizations, and second, on the global level, we do a search rather than just a simple averaging. And we perform some experiments using the language models of different sizes. The first is the robot A, 3 and 15 million. And against both the gradient-based methods and gradient-free methods. And as we can see here, our scheme, FedBBT, is able to achieve higher accuracy than gradient-free baselines under both IID and non-IID settings for all datasets. And actually, it can even achieve decent performance among gradient-based methods here. And of course, we also show here that simply by combining Fed averaging with BBT cannot achieve decent performance, highlighting the necessity of the global searching parts without beyond basic averaging technique. And we further do some experiments using a larger model, the Llama 2 7 billion. And we can show here it also improved the accuracy significantly compared with the gradient-free baselines and achieve comparable accuracies with the gradient-based methods in most settings. And more permanently, it reduced the communication cost of one device in one round from nearly 2 gigabytes against the p-tuning scheme to just the 4 kilobytes, because the gradient-based method, we need to sync the parameters, sync the gradients. Well, for this technique, since it is gradient-free, we only need to transmit the local distribution information that is far smaller as compared with the encoder parameters. Okay. And now, since we talk about the training part, now let's move to the inference part. The new trend of inferencing using the large language models beyond the basic inference is this retrieval augmented generation. Some basics of RAG, retrieval augmented generation, is that now we have 3 models essentially. One is called embedding model. This model is the very base for the retrieval augmented generation. It's gonna vectorize a candidate database consisting of many documents so that it's gonna be easy to search for the information chunks that will be relevant to an input query. For example, it's gonna return the top 50 candidates from a document with regard to a specific query based on the embedding retrieval scheme. And now then it's gonna give us some relevant documents, but since those documents are retrieved based on distance metrics with regard to the embeddings, they may not be that accurate. So we can consider this part as a rough selection of relevant chunks. So in order to refine it, say we want to select the most related 5 out of the 50 candidates. Most of the time, we have a ranking model or we say refinement model that is trained in a different manner as the embedding model. For example, it can be trained as with just telling the relationship between 2 inputs. That essentially is more accurate than relying on distance metrics within the embedding space. So there will be a ranking model, refinement model for refining this initial rough candidates. And finally, of course, we have a generation model that is the large language model backbone we're going to rely on to give the answers to the queries, and combined with those 5 chunks of refined documents as the prompt and context to this generation model for the final answer generation. So as we can see here, there are 3 stages. The first being the training and fine-tuning all those 3 models. And second being vectorization of the database and the retrieval. And the final is the retrieval, augment, and generation, RAG. So if we talk about federated RAG, actually all components of the RAG pipeline we just mentioned can be federated. For example, we can federated train those embedding and ranking model. Here I gave a simple experiment using 3 data sets for training a embedding model, and with a centralized data set and a federated training methods for the embedding model training. And as we can see here, the federated result is better than each individual sites. And that is also, we can achieve a similar or close performance as compared with the embedding model trained with centralized data. And not only that, we can also federate the process of pre-retrieval query modifications. We can make them personalized to each site. We can federate the retrieval parts, meaning that we collect the relevant documents from different sites and federate them together at the server. And also we can do the post-processing way, post-processing in a server side and in the federated side, and to get the refined documents. So as we can see here, the federated large language model training and inference can be queried plus the refined documents fitted to large language model for generations. And the final inference stage can also be federally trained. Say the final large language model can be federally trained. Either they gonna use one single large language models, or each site can even have its own large language model for generation purposes. And those size large language models can even combined as a whole mixture of expert model via gating layers. So all those, the entire pipeline of retrieval augmented generation can be federated from the base model training to the retrieval process, and finally to the generation part. And finally, let's talk about the real life federated studies. And because federated learning is serving the practical service. So without real life study, federated learning will contribute a lot less meaningful to the community. So here I want to introduce our NVIDIA Flare as the backbone or as the platform for federated learning. So NVIDIA is the open source SDK for federated learning that is model agnostic. So any model can be adopted, either it's language model or healthcare or traditional model, say tree model, XGBoost for financial tabular data, or automated driving or monitoring. Everything, any model, AI model can be adopted to NVIDIA. And what NVFlare provides is the federated, orchestrated workflows, a runtime environment, and many privacy preserving capabilities provided by algorithms and also the hardware environment, things like confidential computing. So our Flare platform is Apache license, allowing also the commercial usage, and is widely available in GitHub. And talking about the security and data privacy insurance mechanisms, we have multi-layered security features to protect privacy, from the user identity to communication security to user-defined security policies, and the privacy-preserving algorithms, as mentioned, differential privacy, homomorphic encryption, those are software-based, algorithm-based, and the confidential computing environments that is hardware-based. High level, we enable the data privacy architecture by using privacy filters. It can depend on the scope and in key value pairs such as datasets and the data kinds. And we can inject the encryptions and differential privacy using this filter mechanism, meaning that whenever there is data communications between client and servers, before and after the data communications, we can reinforce the filters to filter out the data, to encrypt the data, and to inject the noise to the data before it leaves the client side and it leaves the server side for communications. So with that, we can enable several data privacy mechanisms during our federated learning process. And as I mentioned, our platform is algorithm independent and data modality agnostic. We can do image tasks like segmentation, classification using CNNs. We can do language processing using smaller models like BERTs, and also large language models with a billion level model scale, either supervised or parameter efficient fine-tunings. We can handle time series data, tabular data, and multimodal data with different various algorithms. And some use cases and integrations are listed here. We have several applications and contributions from different collaborators, and many of them are medical related, and also the large language models and NLP researches. And we also have integrations with popular medical image analysis framework Mo9, our generative AI platform Nemo, and also other federated learning frameworks like Flower. So another thing I want to mention is that the usage of NVIDIA is pretty simple. If your local training scheme is already Lightning based, then it can as simple as adding 3 or 4 lines of code. First by importing our NVIDIA Lightning API like this, and then the API will automatically patch your own local trainer, and then you just wrap everything, all the training schemes with this while Flare is running, and then all the other stuff will be automatically taken care of with our Lightning API. And of course, if your model is not written in a Lightning PyTorch Lightning, we also have a regular client API that is a little bit more complicated as compared with Lightning, but still very simple. You can, beyond the Lightning, you can just receive a global model and do whatever needed to load the global model to continue the training. And then after your local training, you just wrap your local models in this FL model data structure and send it back to the server. So we believe it's still pretty easy to use. And yeah, I encourage everyone to give it a try. And yeah, talking about foundation models and large language models, there are some special support. First of all is the model size, because as we talk about in the beginning, the large language model can be huge. The 70 billion model with the compression leads to about 130 gigabytes. And while the gRPC limit is just 2 gigabytes. So it's with our previous capabilities, this is something that is not be able to be handled. So in order to transmit the large language models for supervised fine-tuning, we now support large object streaming. It's gonna automatically split and assemble large messages to chunks for transmission. And we actually test it over major cloud service providers across the globe. We host one server in Asia, in the West US region, and 2 clients, one in US and the other in Europe. And then the clients will receive and send mock models in about 100 minutes. And we have some statistics to showing the capability of this feature. So in conclusion, there are new challenges in this foundation model era. And of course, there are new opportunities for federated learning. In this new era of foundation models, federated learning faces various training scenarios and settings that does not exist in previous large language deep learning models. And there are multiple constraints over the training processes, and there are new collaborative training and inference patterns to consider. But despite that, despite all the challenges, federated learning still enables adapting large language models with privacy in mind, that we can have multiple data sets that's gonna benefit the large language models towards accuracy, towards robustness. And we can fine tune those models with federated learning, and that can utilize diverse distributed data sets. And not only that, federated learning can help collecting diverse informations from inference, just treating them as a black box, and for inference, using retrieval augmented generation. And beyond the data and beyond the information collectivity, the federated learning can also help gather computation powers from many participants globally to solve the hardware resource, computation resource needs from training the large language models. And in the last thing I want to say is that with the old solutions to tackling the new challenges needs to be enabled by a solid backbone, the solid platform. And with FLIR, we want to enable the real-world collaborative large language model training with massive models, hundreds of gigabytes, so that the next generation of large language models can actually benefit from the collaborative efforts across the entire international collaborations. So thank you, and feel free to try out with FLIR in our GitHub page. And if you have any questions after this talk, feel free to reach out to me. Thanks.
Thank you very much for the great talk. So please, if you have any questions, do not hesitate just to unmute yourself, and then you can ask your question. I'd actually start with two quick questions. So the first one, what I was wondering, do you have actually an example of a large language model or foundational model that was trained using federated learning, but like using federated learning on some private data, and due to access to this private data, that would be actually better than any other centralized LLM for some specific tasks?
Yeah, that's a very good question for federated learning. To be very honest, I'm not aware of any such models at this time. Yeah, because here we show the capability of doing that. But so far, I'm not aware of a large language model trained really in this way. And because to train a large language model, it involves very significant effort and commitment. So I guess that is one reason for that people may be very cautious to start such a large scale study. And yeah, a lot of, I would say, interest need to be negotiated to start such an effort. But so here for FLIR, we show our capability of doing that, but we didn't actually perform a real life study, especially with restricted local data. And having said that, I know I'm aware of a global collaboration that is ongoing, I think, but using a federated learning mechanism to train a large language model by utilizing the hardware resources from from several sites. But my understanding for that study is that the data set used is the same. So essentially, everybody downloads the same data set and collaboratively train a model together. That is something we can consider it as a data parallel. And yeah, so that each site will not need a too much computation that is that can be unaffordable for a single site. But yeah, of course, I definitely look forward to a real life study and real life model training with the restricted data set from each individual sites, and everybody pool their data sets and pool their computation power together to build such a large language model.
Thank you. Is there any other question? Okay, there is a question from Shingu.
Yeah, I can talk.
Please go ahead.
Questions. Yeah, thanks for the nice talk. Yeah, I just wonder the detail about the reg, because the formal federated learning structures clients does submit model updates, and for the RAG in federation setting. I just wonder how the pipeline and data flows and what is the roles of clients. Yeah, could you please tell a little bit about more? Thank you.
Sure, sure. So for the FedRAG, I mean, it is, I think, let's see. Yeah. So FedRAG, if we take a look at this pipeline, and at different stages, we're gonna talk about different patterns of federated learning or federated, let's say, federated information collection in a sense. So if we talk about those three models, embedding model, refinement model, and the generation model training, those are federated learning, right? So we train those three models locally, and then federatedly we can improve their performance. But if we talk about other stages of the rack, for example, the retrieval of relevant documents, federated learning here is more towards federated information collection, if we think about it. So essentially, it's collecting relevant documents from each individual sites and aggregate them together and in a reasonable fashion. Either it is ranking those relevant documents again, or it's processed using other more advanced techniques. But in this sense, it actually doesn't involve a learning or parameter updating. It's more like collecting the necessary or helpful information from different sites so that the eventual refined documents refine the context that will be helping the final generation process will be of better quality because it's getting the information from several sites rather than just relying on one single site or one say just an online database.
Oh,
And yeah, so it's for RAG, it includes both the federated learning and federated computation or information gathering. So I think it's extending the federated learning horizon beyond just the learning model. Thanks.
okay, thank you.
Any other question? Let me ask, yeah, I have one more. I wanted to ask, so based on my understanding, like majority of these approaches are applicable to like a cross silo FL where you don't have that many clients and also like each client has a significant resource compute. So my question would be like, do you think that this is actually scalable to cross-device setting where you have very limited clients? Where like, do you think that even like this, like a limited clients could pull enough resources and provide their private data to also be able to do I don't know, like a fine tuning or even maybe like a pre-training of LLMs?
Yeah, I think that's is something definitely feasible. Yeah, one example, of course, is this black box tuning. Even if you have just a cell phone, you can do that because the prompt encoding part is very light. And yeah, if we targeting not cell phone, but the devices with decent computation power, like our workstations with a decent GPU on them. And of course, one such machine may not be able to perform training of a large language model, or may not be even be able to perform inference, right? There's definitely a possibility for to gather the computation power from say several workstations, such that they will be able to perform, to host a large language model for inference or to perform fine tuning. And the way of doing that is that as we know, there are already techniques supporting, say, training a large language model with only one GPUs. I'm sure I'm sure most people have heard that. And the mechanism for that is that by offloading part of the majority of the large language model to memory or to CPU, to memory or to storage, and only computing, say, one layer of the large language model each time, and swapping this back and forth. And similar idea can be implemented with federated learning. We can just deploy part of the large language model to one device or one GPU. And the federated learning server will orchestrate the data flow during the process. As one computation is finished, it's gonna forward to the next one to process. And in this way, we can enable the utilization of our existing computation devices that are of less computation power as compared with the, say, H100 to train the large language model. And in this way, we can gather what we already have in a federated way, such that the local fine-tuning or local inference can be enabled.
Good. Thank you. I can see that there's one other question in the chat, but I think in the meantime, it already got answered by Holger. I don't know whether Zikai, do you still have another question for our speaker?
Oh, yeah. My question kind of solved by Hopper. So my question is like whether the prompt training based method perform much better than LoRa based method from the table, like 2% accuracy improvement. So my question will be, where is still worth to working on the LoRa based method?
Sorry, I didn't follow your last sentence. Or will it worth to what?
Still working on the LoRa-based method for like
LoRa-based method?
yeah. So
Yeah,
that's my question.
Yeah, I definitely think so. Because yeah, if we consider like prompt tuning, adapter, LoRa, all of them are actually options for a parameter efficient fine-tuning category or family, right? So it really depends on your task, and I believe the downstream task you're talking about. Some of them will perform better, and we will never be certain that which one will perform better, right? It always needs worth trying and testing to select the most efficient and most suitable one for the downstream task. So yeah, I definitely think yeah, when we talk about some different options within the PEFT family, it was trying different options out on your downstream tasks. Yeah, so one may perform better than other for one task, and yeah, vice versa for different task. The other one may perform serve your purpose best.
All right, thank you so much.
Thank you.
All right, so I think we are well on time. So thank you, Ziyue, again for a very nice talk. And thank you all for joining in today. And have a great rest of the day. And please, Ziyue, please don't forget to send me your slides. I'll post them right away. Thank you very much.
Thank you.
Goodbye.
Right.